Hello everyone, I'm going to talk about a part of my thesis work that is entitled Study of Absorption of Dexamethasone on Iron Nanoparticles Stabilized with Glycine. My name is Azury. I'll begin with a brief introduction. Different studies suggest that the iron nanoparticles could have biomedical application, but there is limited information of their use in drug delivery, despite their potential due to a high surface to volume ratio. Research on this application is still scarce. Functionalizing the surface of magnetic nanoparticles reduce toxicity, increase surface area, and enhance stability through surface charge. Glycine, the simplest amino acid and dipolar ion in solution, interacts with the nanoparticles and improves their biocompatibility due to its biological nature. In liquid-solid mixtures, understanding absorption kinetics is crucial for assessing process rates, mass transfer limitation, and the effects of the absorbent's properties. This study also first insight into the specific absorption mechanisms between absorbent and adsorbed. Various mathematical models have been developed to analyze solid-liquid interaction and the dynamics of absorbed complexes. Considering how absorption reaction rates depends on the concentration of the absorbed and absorbent. In this report, the results and absorption studies of dexamethasone, which is a drug used in the treatment of COVID-19, on the surface of iron nanoparticles and using functionalized iron nanoparticles with glycine at different concentrations are present. Langmuir and Freundlich absorption models were analyzed to fit the results obtained by UVB spectroscopy. And for the part of materials and methods, this part corresponds to the synthesis of iron nanoparticles. The iron nanoparticles were prepared by the chemical reduction method described by El Jamal et al. This method consists of preparing two solutions, one of ferric chloride and other of sodium borohydride. The ferric chloride solution was added to a flask with a constant stirring speed and nitrogen flow. The system was maintained at temperature of 20 degrees, and then solution of sodium borohydride was added to the flask, and the reaction was maintained for 20 minutes. And the nanoparticles were separated with a nylon membrane and washed with acetone. And once the iron nanoparticles were obtained, and they were dried under vacuum. These iron nanoparticles present a black color. And the methodology for dexamethasone absorption on glycine stabilized and unstabilized iron nanoparticles. And I forget mention that the glycine is added in the flask for the stabilized iron nanoparticles before adding the reduction agent. This is the solution of sodium borohydride. Now, the methodology for dexamethasone absorption on glycine stabilized and unstabilized iron nanoparticles. In this part, studies of the absorption of absorbed dexamethasone on the surface of iron nanoparticles were performed by monitoring the concentration of non-absorbed dexamethasone at different absorption times, and the concentration of dexamethasone was monitored monitored by UV spectroscopy. And the for these studies, different amounts of iron nanoparticles were placed in the quartz cell, to which 3.5 millimeters of a 1 molar solution of dexamethasone was previously added. And the bubbles were removed like this. And these measures were performed at different absorption times and with 30 minutes lapse between each one. And this procedure was performed for 3 samples, for eh, 4 samples, iron nanoparticles and iron nanoparticles with glycine with 3 different concentration of this glycine. And now for the results and discussion. In this part, we can see send micrographs correspond to the iron nanoparticles stabilized, unstabilized, and stabilized at different amounts of glycine. Uh, okay. And from these micrographs, shows that the particles present a quasi-spherical morphology in chain type arrangement due to their magnetic nature. However, this arrangement differs for the iron nanoparticles with glycine 3. This is the a major amount of glycine utilized. And for the first two first two samples with lysine, the average size decreased, but according to what is observed on 10 micrograph of iron nanoparticle with glycine 3, there seems to be formation of a larger agglomerates resulting in a larger particle size, which is due to the excess of glycine. And the iron nanoparticles without glycine present average particle diameters of 121 nanometers, while iron nanoparticles 1, 2, and 3% average size of 115, 85, and 112 nanometers respectively. Or on another hand, in this figure, correspond to the zeta potential analysis, and this figure shows the plots obtained of this technique. And all the samples present negative surface charge. And we can see this in these graphs. And in the case of the iron nanoparticles without glycine, due to the, due to the formation of a slight oxide and or oxyhydroxide layer, typical of these nanoparticles, is due to this negative charge. And in the case of the iron nanoparticles stabilized with glycine for the sample 1, 2, and 3, it is likely that the oxide and or oxyhydroxide presents in this draw. Um, this layer is interacting with the amino group of the glycine like this, this way. And so the carbonyl carboxyl group of glycine gives them the negative character of the surface for these samples. In the figure 5, the diffractograms of the iron nanoparticles uh, on stabilized and stabilized with glycine are present. We can see that this graph, this diffractogram, sorry, show the diffraction peak corresponding to the 110 plane of the iron BCC structure. Good, good crystalline quality is observed at the width of this peak. And, however, the less intense peak corresponds to the in 220 and 211 plants are run by the presence of glycine in like this. Um, from these results, it's confirmed that the layer of oxides and hydroxide mentioned previously is thin and is not present in significant amounts to modify the structure. For the most intense diffraction peak correspond to the 110 plane, the crystalline size of iron nanoparticles and the iron nanoparticles with glycine 1, 2, and 3 were calculated with the Scherer equation, which were 9.55 and 7.81, 6.65, and 5.54. Therefore, the use of the glycine as a surfactant decreases the crystalline size of iron nanoparticles with respect to those that are not functionally safe. And now for the FTIR spectroscopy result, we can see this figure in this part, figure 6. This figure shows the um, spectra, the FTER spectra of stabilized and non-stabilized iron nanoparticles. And according to Larkin, metal oxides of various types have strong bands correspond to the metal oxygen metal group in the region between 800 to 200 centimeters. In this part, we can see this band correspond to the iron and oxygen, and we can observe that this peak is less intensity in the other samples. So the glycine help to reduce the oxide percent in these samples. Iron nanoparticles with glycine 1, 2, and 3. And now for the absorption studies by UV spectroscopy. Uh, the graph of dexamethasone not absorbed on the unstabilized iron nanoparticles disease shows that the dexamethasone was not absorbed on the surface of these nanoparticles. So, a variation of the glycine concentration in the reaction of the iron nanoparticles is necessary to functionalize the surface of this in such a way that its interaction with dexamethasone. The graphs of dexamethasone not absorbed of the iron nanoparticles 1, 2, and 3 is present in these graphs. And from these results, Langmuir and Freundlich models were used for the analysis of dexamethasone and absorption on the different samples with iron nanoparticles. These models we can see in this part in their form linearized. This the Langmuir model assumes that the absorbent surface is homogeneous. All active sites present on the substrate have a similar energy or affinity for the analysis under investigation, and therefore absorption is homogeneous and occurs without any interaction between the analytes absorbed on the absorbent surface. And this the linearized equation. And one more in this part, it show the Cronlich model, and it is used when the absorption sites cannot be hypothesized as uniform and there is an energy distribution. It is applied when heterogeneous absorbents are considered, and it's expressed in like this form. From these results, we have and this in this table resume the different parameters of these models and the results of R squared from these fits. And we can observe that with the presence of the glycine in the different samples, improve these results of these fits. And we can observe in this table, but the Langmuir model is best for this to release these fits. And the conclusions from this information is according to the results obtained first, according to the results obtained by SEM and X-ray diffraction, is demonstrated that the use of glycine in the synthesis of iron nanoparticles modifies the average size of the nanoparticles as well as the crystalline size. However, in the sample with higher amount of glycine, that increases the average diameter is observed, but not in the crystalline. So there is probably an excess of glycine that also modifies the chain type structure in which the nanoparticles as arranged. And secondly, it is concluded from the zeta potential analysis that with a low amount of glycine, then nanoparticles are more stable in solution. Also from the results and those obtained by the FTIR is demonstrated that the use of glycine in the synthesis of iron nanoparticles decreases the amount of iron oxide formed on the surface of the iron nanoparticles, but the presence of oxyhydroxides that interacts with glycine is maintained. So the carboxylic acid group of glycine allows the interaction with the hydrogens present in the functional groups of dexamethasone by possible hydrogen bonds. And according to the obtained values of square air, it is observed that the Langmuir model fits better to the obtained data. By the values of the maximum absorption capacities is concluded that the use of glycine is higher amounts improves the absorption of dexamethasone on iron nanoparticles. And thank you very much.